Welcome to our presentation, everyone. I'm Hannes and I'm in group number 1. My fellow teammates are Magda, Natalie, Drew, Julia and Darek. Let's begin. The outline for our presentation is as following. We'll start with information about the models, then present the distribution of the wind, power production curves of the two Vestas models, and then continue by showing the results of the yearly production of the nacelle at 60, 80 and 100 meters. Finally, we observe the influence of roughness and end with a short conclusion. Our project is focused on a Vestas V80 and Vestas V90 wind turbines. Here are some parameters of the two models, and under the parameters we see the power curves as given from the manufacturer. As we can see, the wind distribution measured at 40 meters with a roughness of 3 follows the Weibull curve, and the average wind speed measured by the mat mass is 8 meters per second. By using the online calculator found at windpower.org, we found the average wind speed at 80 meters to be 11.12 meters per second using the roughness factor 1. This slide illustrates the wind distribution of our nacelle. As you can see, it follows the Weibull distribution. We calculated the power production for Vestas V80 according to the equation of the power curve slope. Then we made a graph of the power distribution. The yearly production using this model comes out to be 8.14 gigawatt hours. For the Vestas V90, we used the same method to evaluate the power distribution. We obtained a yearly power production of 9.32 gigawatt hours. Here we are comparing the yearly power distribution of the nacelle at 60 and 100 meters height. As one might expect, the power production grows with elevation as shown on the graph on the right. The situation is the same in the case of Vestas V90, as you can see from the graphs. Here, we are given new wind distribution data of east and west blowing wind. By using the same approach as before, we plotted the wind distribution. As we can see, in this case, it does not follow the Weibull distribution. However, this does not have any importance for the power calculation, since the wind follows various patterns in different locations. Darek, what are you doing up there?
What the wind today?
Let's keep going. The yearly production of the Vestas V80 wind turbine at 80 meters is much higher when using wind from the west than when using wind from the east, 9.53 versus 2.79 gigawatt hours respectively. Here you can see the influence of the roughness factor and how it affects the yearly power production. Which leads us to the conclusions. From our calculations, we can conclude that as we go higher with the position of the nacelle, the wind velocity will increase and we therefore obtain a higher energy output. Another observation is that the lower the roughness class, the higher the total energy output, as the wind is being slowed down less. With our given distribution, more power production can be achieved with westerly wind. By using the Vestas V90 turbine, we can achieve maximum power at lower wind speed.
Hey Hannes, why don't you take a break for a while?
Thanks, Natalie. Bye, everybody.
Let's move on to waves. We'll be talking about wave climate. We'll also talk about yearly production for an overtopping device and a buoy in 2 different wind scenarios. Here's a table of the calculated values for wave climate in a kilowatt per meter wavefront. You can see here that we have the greatest power production potential in 5-meter waves. Over the course of a year, this 3D graph shows that the greatest power production for an overtopping device will come from waves 5 meters tall over a period of 9 seconds. Our total yearly production will be about 21 gigawatt hours. However, if we only consider winds blowing from the west, we will only produce approximately 13.5 gigawatt hours per year. Like in the previous slide for the overtopping device, this graph shows that greatest power production for a buoy-type device will come from waves 3 meters tall over a period of 7 seconds. Our total yearly production will be roughly a quarter of a gigawatt hour. These slides are going to look very similar. However, this graph uses data from a wave distribution table specific to our group, group number 1. This graph shows that the power production is greatest at a wave height of 5 meters and a period of 8 seconds. The yearly power production will be roughly the same as before at 21 gigawatt hours. Here we can see that the buoy's yearly power distribution graph for our group is very different than the one calculated from the common data. It has a very narrow peak production point at a wave height of 5 meters and a period of 8 seconds. It will only produce about a half of a gigawatt hour over the year. On this slide, we have calculated the values for wave climate in kilowatts per meter. The greatest power production potential is in 5-meter waves. Here are our conclusions. The main point that you want to take away is that the overtopper system has a yearly production yield 40 times higher than the buoy system.
Thank
Thank
you
you
for
for
your
your
attention.
attention.